So Chase, I like example 4. I like example, specifically, I like 4B and 4C. What's different between 4B, 4C, and 4A? If you look, I've stuck extra vertical forces on there. So example 4 says, find the maximum force of friction between the mass and the ground for the following objects. Technically, this would be mu static if I went back to that little rant I did last class, but I've said to you, we're just going to pretend that all the mu's are the same. In other words, how hard would I have to pull to get these objects to start to accelerate? I'm going to zoom in. In fact, I think I can zoom in a bit more, Mr. Dueck, on example A. For all of these, we're going to be saying, well, friction is mu times the normal force. We're going to start there with our friction equation. And we'd like to calculate the maximum force of friction. You know what it was a good job for? A free body diagram. What are the forces acting on this mass? Get the obvious one. mg. What else? And this is where I always say, is it sinking into the ground like quicksand? Is it flying through like Superman? There's a reason I go systematically. And we would say, no, it's not. So vertically, the forces must be, I'm looking for it begins letter B, balanced. So is the normal force going to be bigger, smaller, or the same size as mg? Eyeball it. Oh, Fn, Mr. Dueck. Okay. And then technically, we're pulling it to the right. I'm going to ignore this. This is enough for us to calculate the maximum force of friction. Now, if we're not pulling on it at all, how big is the force of friction? 0. If I pull with 1 Newton to the right and it doesn't move, how big must friction be to the left? Exactly 1 Newton. If I pull with 3 Newtons to the right and it doesn't move, Jared, how big must friction be to the left? Exactly 3 Newtons. It's got to be balanced. What's the biggest friction can be? That's what we're calculating here. So, friction equals mu 0.35 times the, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force is the same size as the normal force, McKenna? So it's going to be 0.35 times 8 times 9.8, which is what? Maximum force of friction is what? Sorry? 27.4? Is it 27.44? Yeah, that's what I figured. So 27.4? 27.44 exactly. If I pull with 27.43, it's not going to accelerate. If I pull with 27.44, I'll feel it right. It's ready to move. And as soon as I pull with 27.44000001, now we would have unbalanced forces. It would accelerate. And then in real life, friction would get smaller. But we're not talking about that right now. B. We're still going to use the idea that friction is mu times the normal force. You don't need to rewrite it if you don't want to because you have it on A, but since I've scrolled over, I'll rewrite it. Emma, what are the forces acting on this? Get the obvious one. I always start there. Is it sinking into the ground like quicksand? Is it flying through like Superman? Then there must be a force pointing up. That's going to be the normal force, the ground. Is the normal force in this case going to be bigger, smaller, or the same size as mg? That's the question. Why must it be bigger? Because not only is the normal force having to cancel out gravity, what other force is it having to cancel out? 55. In fact, I think it's going to be 55 bigger than gravity. Is that okay, Jared? I'm going to exaggerate it so it catches my eye. So I would say this. Friction equals mu times the normal force. I don't know the normal force. And it's not mg. This is why anytime somebody says, oh, friction equals mu mg, I snap in a nice loving teacher kind of a way. How am I going to figure out the normal force? Well, Chase, are we sinking into the ground like quicksand? Are we flying into air like Superman? Then the forces are, I'm looking for the begins letter B. Here's what it really means. Everything up has to equal everything down. What arrows are pointing up? Please tell me. Over here in the margin, let's write down normal force, and then has to equal, what arrows are pointing down? There are two of them. Is it 55? Okay. You said mg and 55. When you say the word and, what mathematical operation do you really mean? Huh? What? So. Does that make sense? Has to be. We're using Newton's first. So what I'm going to do is, instead of the normal force, I'm going to put in brackets mg plus 55. That is mu times the normal force in disguise. If we actually crunch the numbers, it's going to be 0.35, and then in brackets 8 times 9.8 plus 55. I would strongly recommend you all try typing that into your calculator, Sky, because there's brackets and funkiness there, just to make sure you get the right thing. Mr. Dueck, do that one in your head. Well, maybe. 8 times 9.8 is going to be 80 minus 1.6. It's going to be 78. Nope. I lost a decimal somewhere. It's Monday morning. So 0.35 bracket 8 times 9.8 plus 55. And that's probably how I choose to type it. You get 46.69, 46.7 newtons. Did friction get bigger or smaller when we push down on the object? Bigger, which is what happens. This is why I think I gave you the example last day, pushing the wooden benches across the gym floor. If somebody comes and sits on it, friction gets dramatically bigger, and so it comes to a stop pretty quickly. I think in C, friction's going to get smaller. Let's find out. Have you all already written friction equals mu times the normal force somewhere at the top there? I'm not going to rewrite it then. I'm going to go straight to plug and chug, but this is still a job for a free body diagram. What are the forces acting on this one? Get the obvious one, Ethan. Welcome back. Get the obvious one. Yes. Is this sinking into the ground like quicksand? Is it flying through like Superman? What that really means is vertically the forces must be balanced. I'm missing a normal force, but this time is the normal force going to be bigger, smaller, or the same size as mg? And how do I know? It's going to be smaller because now the normal force isn't have to cancel out all of gravity. Someone else is canceling out 55 newtons worth. I'm going to really exaggerate it. This is why I said to you, Serenity, I do my free body diagrams roughly to scale. If you want the actual accurate scale, for example, for B, what I should have done is measured this arrow, measured that arrow, and this should have been as long as both of them added together. I don't do that much. If they're equal, I'll make them the same length, but if they're not, I'll exaggerate it so it catches my eye. So what did you all say? The normal force in C, bigger, smaller, or the same size as mg? Smaller, I'm going to really exaggerate it so it catches my eye. I'll notice that. And so we would again say friction equals mu times the, I don't know the normal force. Are we sinking into the ground like quicksand? Are we flying into like Superman? Really what that means is everything up has to equal everything down. Which arrows do I have pointing up, Jared? There are two of them. So over in the margin, you know what? How about right here? I'm going to make a little note. Everything up, you said and, I say plus, yes? Equals, which arrows do I have pointing down? How would I get the Fn by itself? How will I move that plus 55 over? So, in brackets, I'm going to have mg minus 55. You know what? If you have a good calculator, like I've suggested, you might even be able to just backspace and change the plus sign to a minus sign. That is just so satisfying to me. If you don't have a good calculator, I weep. and I get, 8.19? So, in conclusion, to get A accelerating to the right, you would need to pull with more than how many newtons? And I'll even put it 27.44. I think that's what it was, yes? To get B accelerating to the right, you would need to pull with how many newtons? (46.69), yes? And to get C accelerating to the right, you would need to pull with more than 8.19. And so what I'm going to start to do in the future more and more is I'm going to muck around with the normal force. I'll add extra vertical forces into the question. As long as you're reasonably careful, as long as you can remember, Jared, that everything up has to equal everything, which is really what I'm saying when I'm saying forces are balanced, because I don't think I'm going to give you something sinking into the ground like quicksand or flying here like Superman. Then you can figure out the normal force with minimal, one line of work. Jimmy, is that okay? Yeah. Good, turn the page. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. It says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, and find the acceleration. I might just give you part D as the question, because to do part D, you'd have to walk through part A and part B and part C. Lillian, are we doing the same thing for both of these? Yeah. I'm going to do my old reliable draw a line down the middle of the page trick. In fact, I'm going to do these at the same time so you can kind of see the slight differences between each step, except I'm not going to do part A first. Do you know how I'm going to start out these questions? This might be a good job for? I'm going to do a free body diagram first. So what are the forces acting on the left-hand side? Serenity, get the obvious one. Good. Is it sinking into the ground like quicksand? Is it flying through like Superman? No. Is the normal force the same size as mg in the left-hand one? I think so, because everything down, Jared, equals everything. Or everything up equals everything. Then we have this force to the right. Who remembers, what did we call a mystery force coming from off the page that we didn't want to make a story up for? Yeah, the applied force. So I'm going to draw an arrow, and next to the 20, I'll put that equals F applied. Is there friction in this question? Yes. How do I know? On the surface, they put a coefficient of friction. It's fairly slippery, but still some friction. Which way will I point friction? Left. And I'm pretty sure it's smaller than F applied, so I'll make it kind of obvious. Good. Sean, on the right-hand side, what are the forces acting on to get the obvious one? What else? Bigger, smaller, or the same? What? Bigger, because it's canceling out that extra 15, okay. We have F applied. And we have friction. Now, in the right-hand diagram, I gotta be honest, Chase, I'm not sure F applied is gonna overcome friction. I'll know I'm wrong if when I solve for A, for acceleration, I get a negative answer. If I get a negative answer, I pick the wrong winner. Friction is winning, not F applied. And it's pretty obvious. It kind of screams out at you, huh? Where'd this negative come from? Wrong winner, but it's an easy fix. Go make your winners, losers, losers, winners. Zip, zap. It's pretty quick. Okay. A says write a vertical force equation. Okay. Serenity, you did the left-hand one. Are we sinking into the ground like quicksand? Are we flying through like Superman? No. Vertically, forces must be. I'm looking for it that begins letter B. So everything down, what's the only arrow pointing down? Equals everything up. What's the only arrow pointing up? So here is my vertical force equation for the left-hand side. Sean, let's write a vertical force equation for the right-hand side. Are we sinking into the ground like quicksand? Are we flying into like Superman? That really means that everything up has to equal everything? What's everything up? Keep going. I'm going to go mg plus 15. Did they say that they wanted me to calculate anything, or did they just say write an equation? Have we written an equation? Next, B. Serenity, what does B want me to find? The force of? Sean, what does B want me to find? The force of? Well, for both of you, it's still going to be mu times the normal force. Mu times the normal force. Hey, what's mu? I don't know. What's mu with you? Oh, what's mu in this particular question, according to the little picture they gave me? 0.12? Okay, so I'm going to say friction is 0.12. Oh, Serenity, I don't know the normal force. Oh, but look, 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 look. I don't know the force the same size as the normal force. Which force is the same size as the normal force? mg. So it's going to be 0.12 times 10 times 9.8. I can do that in my head. It's going to be 98 times 0.12, which is going to be 9.8, plus 1.96 is going to be 11.76. Yes? No? Am I off? No? So somebody could have verbally, when my eyes were closed, said yes? Because I got it to 4 sig figs? Okay. On the right-hand side, friction is still mu times the normal force. I don't know the normal force. Oh, but look, look, look. Ooh, I don't know another force the same size as the normal force, but I know some forces, plural, the same size. What can I replace the normal force with? Or as I like to say, mg plus 15. So it's going to be mu bracket mg plus 15. It's going to be, what's mu? 0.12. M 10 times 9.8 plus 15. Do that one in your head, Mr. Dueck. Well, okay. 9.8 times 10 is 98 plus 15 is 113. 113 times 0.12 is going to be 11.3 plus 2.26. It's going to be 11.3, 13.3, 13.56. And it's the force units, newtons. Serenity C says write a horizontal force equation. So in my free body diagram, who's probably winning horizontally? I think that 20F applied. Who's probably losing? What's winner minus loser always equal? What? MA. So I'm pretty sure it's going to be F applied minus friction equals MA. What about your horizontal force equation? Who's winning? F applied minus, who's losing? What's that going to equal? Mr. Dueck, how come we have the same equation? Doesn't that mean we're going to get the same acceleration? No, because I think we have a different force of friction. Serenity, what does D want me to find? How would I get the A by itself? What's the M doing to the A? Adding, subtracting, multiplying, or dividing? So if I hear you correctly, and I think I do, you're telling me A is going to be F applied minus friction all over M. I divided by M, and I also put the A equals on the left-hand side because that's our preference. Okay. F applied 20 minus 11.96 divided by 10. Do that one in your head. Okay. It's going to be 20, take away 11 is 9, take away 0.9 is 8.1, take away 0.804? No, am I wrong? No, I'm right. I think I'm right. Is it not 0.804? Am I off? Okay, people looking at me. 20 take away 11 is 9, take away 0.9 is 8.1, take away 0.6 is 8.04. Yeah, 0.80, isn't it? Well, people, work with me here. Give me some feedback. It's an acceleration. Units? Am I wrong? Alex? Is it 0.824? 804? You're wrong. I did it in my head. I'm right. Dumb calculators. Sean, how would I get the A by itself? And again, what I really want you to notice is in terms of physics, these questions are almost identical. We get the same equations. The only difference is pushing down or lifting up changes how big friction is. Is it 0.824? Did I do a dumb mistake? Are you right? Is it?
Well, I got 11.76.
Oh, I wrote down a wrong number up here. Is that what you're saying? That's a 7? Maybe I did. Maybe I did that one wrong. Oh, good gosh, Mr. Dueck. Well, then it would be 0.824. Digital ink. No one saw my mistake. Oh, I'm recording this one for YouTube. I guess they'll find out. Okay, I got to redeem myself. I better double check this one. Was this 13.56 correct? That one? Okay, let's do this one in your head, Mr. Dueck. You got to at least get back on the saddle. It's going to be 20. Take away 13.56 divided by 10. You know what? Let's all do this one in our heads. Put your calculators down. Ready, Alec? It's not that tough. 20, take away 13. 7, take away 0.5, 6.5. Take away that 6.44. And then what are we dividing by? 0.644. It's not that impressive. Dividing by 10, I can do that. See? That's the nerdy thrill. That's the giddy adrenaline rush that I get every time that I do math in my head. And it's an acceleration, meters per second squared. So as far as I'm concerned, I can give you pulling on an object with an applied force, and I can change friction by mucking around with the normal force. And I think that's fair game. I can either have you find the acceleration, or if I go all the way up here, I could have given you the acceleration and asked you to find mu, or the force of friction. You don't need to memorize this. This is just to give you some context. Turn the page. Here's some common coefficients of friction. Some common levels of slipperiness or stickiness, some common mu's. Wood on wood is about 0.25. Wood on wood will slide fairly well. Wooden toys don't have grease in them usually, and they slide okay. Steel on steel is a higher mu. This is why typically for steel on steel, we have to lubricate it. When we add oil or grease, we can get it down to about 0.1. Rubber on dry asphalt, this one really varies. It depends on temperature. On a hot day, pavement is stickier versus on a cold day. So it can be anywhere from 0.4 to 0.7-ish, depending on the circumstances. But what do you notice when it's raining? What happens to your mu? What happens to the coefficient of friction? Yeah, and that's physics. That's nothing to do with your driver skill. All of you are getting your licenses. When it's raining heavy like it was this weekend, slow down. It's impossible for you to stop as quick. It has nothing to do with your driver skill. Friction got smaller. Thank you very much. So slow down. Rubber on ice is terrible. Steel on ice is actually a little better than rubber on ice. All these values, though, are approximate. Can you have a coefficient of friction greater than 1? Yeah, but it's fairly rare. But rubber on glass has a mu of about 2 approximately. So rubber sticks really well to glass. And dragster tires. So a dragster tire has a mu of 2.8. Is that small or is that big? You know what? I heard what you said. I should have said, is that small, is that big, or is that really big? That's really big. Shouldn't a tire with so much friction slow the dragster down? Using principles of physics, explain why a high coefficient of friction is essential for racing. It's very desirable. Nicole, what did I say the hint was? You're back with me? You're not looking at your phone or anything foolish? What did I say was the hint? Draw a. So let's represent the dragster with a dot. Hayden, what are the forces acting on it? Get the obvious one. Yep. Is it sinking into the ground like quicksand? Is it flying here like Superman? So there is a normal force, same size as mg. Let's assume that forward is to the right. So which way do we want this dragster to accelerate? To the. So there has to be a force pointing that way. We would like that. What force is that? It's not F applied. Don't feel bad. I've seen many physics teachers get this. I've argued with people. What? This is why you can't drive on ice. What pushes you forward when you step on the gas, if you look at the car specifically where it's touching the pavement, it's friction. Everybody, friction is what times what? Mu times the... So how can you get a bigger force of friction? Bigger mu. And this is why dragsters do that smoke show before they go. It's not because they want to impress the crowd. What's stickier, melted rubber or non-melted rubber? They're heating up their tires on purpose because that bumps it up even higher, gives them a bigger force of friction. Doesn't make their tires last very long, but you know, at that level, those tires are several, probably $1,000 a piece, and you're going through them once per race anyways. That's why you need sponsors. That's why racing is so expensive. But absolutely, you want a high coefficient of friction for a dragster, not a low one. Very counterintuitive. And you're right, people always want to say, isn't there an applied force or F engine? No, trust me, it's the tires. If it was an applied force or an engine, that dragster could function on ice. It won't. Example 7, and then do I have an example 8? And then I think we're done. No, and an example 9, and then I think we're done. You already watched the balloon behavior last class. Example 7. Force of 120 newtons is needed to push a box along a level road at a steady speed. If the force of gravity on the box is 250 newtons, A, what's the force of friction between the box and the road? And B, what's the coefficient of kinetic friction between the box and the road? What's A asking me to find? The force of friction? Okay. Any suggestions on, oh, I like this question, I like this question. Any suggestions on how I might want to start out? That's a good call. How about a free body diagram? Now, how do I know? I see a whole bunch of forces in this question. I better organize them. So let's represent the box with a dot. Cool. Arena, what are the forces acting on it? Get the obvious one. Okay. And you know what? I'm going to write mg, but I can tell you exactly how they told me. 250. Which also means I can tell you the mass of this object if I need to. How would by the way, what did they give me with that 250 newtons? And what's another word for the force of gravity? No, now. What? No, now. What? Yeah, weight. Okay. So they gave me the weight, the mg. Could I figure out the mass from that 250? If I wanted the mass, what would I do with that 250? Divide by? If we need it, we can get it. Let's just, I'm not going to bother, but if we need it, we can get it. What else? Is it sinking into the ground like quicksand? So there's a normal force. What else? Well, it says a force of 120 newtons is needed to push. So I think that's our F applied. Is there friction in this question? Yeah. In fact, what does part A want you to find? Don't write this down, look up. My first thought would be to go friction equals mu times the normal force. Why can't I do that? Why will that not help me at all? Sam, they didn't give me the coefficient of friction. In fact, what's part B asking me to find? Okay. I haven't finished my free body diagram. Did you see the two key words that make this question solvable? You see it? All of us underline steady speed. I'm going to draw friction pointing to the left, Irina. Is it going to be bigger, smaller, or the same size as F applied? Newton's first, has to be. And so, in your head, without a calculator, how big is the force of friction? The same size as which one? And so I'm going to start out by writing, well, I know F applied equals friction, and wonderfully, they told me F applied. How big is F applied in newtons? How big is friction in newtons? You see that? That's a four-step reasoning chain that we made. And each step, when you see it, is pretty obvious, but to get all four in a row, you got to know your stuff, okay? So, friction equals 120 newtons. Yay! For part B, I wrote friction equals mu times the normal force because they want me to find mu, and that's the only equation that I have with a mu in it. Oh, how would I get the mu by itself, Irina? Divide the normal force over. Okay. Mu is going to be friction divided by the normal force. Do I know friction? How big? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. You know what? I didn't even need to bother figuring out the mass. Well, that was convenient. I mean, it's nice that I could have if I needed it. So that's going to be 12 divided by 25. Dividing by 25 is the same as timesing by 4 dividing by 10. So 4.8, double check me. No, 0.48, sorry, 0.48. Put the decimal in the wrong place. Units. It's a trick question. There are none for the coefficient of friction. And you can see why. It's newtons divided by newtons. Those would cancel. Nothing left behind. Okay? So I think it's fair game. I can ask you to find a coefficient of friction. Get the mu by itself. You'll probably end up dividing by the normal force. You probably won't know the normal force. Oh, but look. Or you might have to do an equation like Jared pointed out to say everything up equals everything down if it's more complicated. Example 8. I like example 8. Example 8 is a nice question. By the way, I'm going to be giving you a whole bunch of homework today. Next class, which is what, Wednesday, I will not be giving you homework. We're going to be watching a short Mythbusters video. We'll be doing one of those stupid fill-in-the-blank handouts to make sure you're paying attention, because that's how I make sure you're paying attention. I will be giving you a bonus challenge that's really cool that you can try, but you'll have class Wednesday to also work on the Lesson 5 and Lesson 6 homework. Dragster's tires accelerated from rest. I've probably mentally underlined from rest to a speed of 32 meters per second and a distance of 64 meters. Cool. A. Mr. Rye, what's A want me to find? Boy. Oh, do you think just reading this question that I'm going to use forces to find acceleration? I don't think I'm going to use F equals ma because I see from rest, I see a V final. I think I'm going to use my good old A equals question mark. VI equals 0. VF is 32. What's that, 64? Give me an equation, get the A by itself, please. So it's going to be 32 squared minus 0 squared all over 2 times 64. Oh, I can do that in my head. It's going to be 32 times 32. The 64 is going to cancel one of the 30. It's 32 divided by 2. 16? Yes? Yes? Cool. B. What's B want me to find? No? What's B want me to find? Yeah, I know. What's B want me to find? The what force? The what force? The what force? The what force? Oh, that's a trigger word. I can go straight to, hey, F equals ma. Did they give me a mass? 540. Did they give me an accelerate? Oh, what did I find in part A? A. Jimmy, you writing this down? I don't think you were. You are? Good. 540 times 16. What'd you get? Are you doing it in your head too? Are we having a little showdown, you and I? Is that what it is? Okay. Is he? What'd you say? Oh, you had to jot something down, or did you do it all in your head? Is it 8,640? Is he right? Oh, it's on. Units? Oh, please, it's a battle of wits with an unarmed man. I can handle it. C. What's C want me to find? Read carefully. Well, friction is mu times, you know, I think I've just reached the point where now I should probably consider drawing what? I think so. I've got room off here in the margin. I'm going to represent this car with a dot. What are the forces acting on it? Get the obvious one. I definitely have gravity down. Normal force up. Let's assume we're accelerating to the right. So winner this way. Who's winning? Yes, no applied force, nothing. What's making this car go forwards is friction. Why won't mu times the normal force help me? I don't know mu. Does that mean I can't do this? Well, let's try writing an equation from here. Who's winning? Who's the loser? It's a trick question. Who's losing? No one. What does winner minus loser always equal? What did we find in part B? MA. What does winner minus loser always equal? MA. But what did we also find in part B? MA. Oh, you know how big friction is? Sean, I'll allow you to give us the answer. Isn't that nice? It looked really tough at first because I don't have a mu. Wait a minute. Actually, I already knew the answer because there's only one unbalanced force, so that must be the MA. Now it wants me to find the coefficient of friction, part D. So, you know what? I have my friction equation written right here. How would I get the mu by itself? It's going to be friction divided by the normal force, where friction is 8,640 divided by, I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Which one? mg, which is going to be 540 times 9.8. I think we're going to get a coefficient of friction bigger than 1. I hope, because these are dragster tires, and I was trying to make this realistic. Dragster tires are sticky. You're going to get a little more than 1.6? 1.63? Irina, units? Are none. Mr. Dueck, would you give us the multiple choice question where you asked us to find mu, and A had like newtons next to this just to really taunt us, and then B had no units? No, I would never try and trap people. No, I would never do something like that, ever. Got the hint there, Sky, I hope? I'm a little worried because, you know, some people in this class will... Okay, last one. I like example 9, Example 9 is a great question. I am going to ask you on your test, I'm going to give you an applied force, I'm going to include friction, and I'm going to give you an extra vertical force, either lifting up like in this question, or pushing down, and I'm just going to say, find the acceleration. Campbell, you know what this is a good job for? Did they give me a picture? I'm going to cheat and just label the picture, which technically isn't a free body diagram, but whatever. Campbell, what are the forces acting on it? Get the obvious one. What else? Bigger, smaller, or the same size as mg? And how do I know? I'll give you a hint. It's not the same size because there's an extra vertical force. I can tell you that. So lifting up, would that make the object press harder on the floor or less on the floor? So normal force bigger, smaller. I'll really exaggerate it. And then I think I have an applied force of 45 newtons. Is there friction in this question, Campbell? How do I know? I'll often just stick a mu somewhere in the picture to see if you're paying attention. So, friction. Who's winning? Probably the 45. Oh, you know what? We're lifting up, which makes friction even smaller. I'm willing to bet it is F applied. So I'm going to go with winner minus, which force is losing? Campbell, my friend. What does winner minus loser always equal? MA, and they want me to get the M by itself, so I'll already go divide by, sorry, get the A by itself, so I'll already go divide by M right now, because why not? So I'm going to get A equals F applied 45 minus mu times the normal force all over 5.8. I'm going to be a bit more careful here. If mu equaled mg, I'd probably just cross out the Fn and write a little tiny mg right above it in that equation. But I'm going to walk over and very carefully, are we sinking into the ground like quicksand? Are we flying to like Superman? That means everything up equals everything. Everything up, it seems to me, is the normal force plus, I've scrolled down, 25. That equals everything down. How would I get the Fn by itself? Boom, minus 25. Your normal is mg. When you're feeling lighter, we're subtracting from the normal force. So, it's going to be 45. Hey, Campbell, what's mu? I don't know what's mu with you. What's mu in this question? 0.36. And then we're going to have m, 5.8, g, 9.8, minus 25, all over 5.8. Get your calculators out. If you want to type this all in one line, is this a fraction? Is there more than one thing on the top? If I don't have a two-level fraction, I got to put bracket around the top. 45 take away 0.36 times bracket. 5.8 times 9.8 take away 25. Close off the mini bracket. Close off the top bracket. Divided by 5.8. And I get, did you do this one in your head? Me neither. 5.782344828. 5.73. Okay. Now, if you don't want to do that all in one step, you could certainly have crunched the normal force and then gone bracket 45 minus 0.36 times answer button, close bracket, divided by 5.8. But you got to be able to handle this either in two steps or in one step. You've got to, it does you no good if you can write down all the right numbers and you're throwing away marks because you haven't practiced with your calculator. So if you need some help with your calculator, you can absolutely ask me in class. 5.78 units, Campbell. It's an acceleration. Yep. By the way, as far as I'm concerned, based on this line right here, I could give you the acceleration and ask you to get the mu by itself. Be in a couple of extra steps, but doable. We watched the baffling balloon behavior last day. What's your homework? Number 1. Number 2, look at that 4-kilogram block. Is it sitting on a surface? So is there a normal force? Nope, don't get normal force loopy and start sticking them everywhere. Here you have gravity and tension. Number 3, your hint is draw a free body diagram on the car, on the drag race car. 4 is good, 5 is good, 6 is good, 7 is good. Are you going to sign them all again? Probably. 8 is good, 9 is good, and 10 is good. Yeah, all of them. I have left you, if you write small, you can do your free body diagrams and your equations right on the sheet. You don't have to. You can absolutely do them on a separate piece of paper. What I'm saying is, though, I don't want to see anybody hand in this lesson with only number answers written down. I need to show work to do these. I can't do them in my head, so you can't do them in your head. You got to show me free body diagram and at least one line of an equation or more. Okay? So you have the remainder of class today, and then you'll have a bunch of time in class on Wednesday as well. Also, almost none of you have handed in lesson 5. I would say that's technically due today. So if you haven't done lesson 5 yet, I would work on that first. If you still haven't done lesson 4, I'd be working on that first. I wouldn't be staring at my phone or anything foolish like that, because that would be silly in the extreme, right?
Yeah.
I'd be putting my, yeah, there you go.